Good evening. Well, I want to welcome all of you guys to this evening. Welcome to the Virginia Living Museum for both our in-person guests and our Zoom friends that have joined us. My name is Rachel Riesbeck, and I'm the Education Director for the museum. I'm really excited to kick off our 2024 Naturally Speaking series with a topic that I feel like is very near and dear to my heart. I'm very fascinated by the oceans and climate change, and of course have grown a new appreciation for fossils since joining the museum a couple years ago. I was able to connect with our speaker, Dr. Adriane Lamb, and I told her that I really wanted her to come speak just because of the title of her presentation, which, you know, I love a good pun, so very excited. And she's got wonderful things for us tonight. I'm going to turn it over to her so she can tell you a little bit about herself and go into some of her research. And then we will end up the night with some questions from you guys. So thanks for coming tonight. And let's welcome Dr. Adriane Lamb.
Thank you, everyone, and thanks for being here. So I'm going to tell you tonight about some of my actually dissertation research. So I'm assistant professor at Binghamton University, and this is the last chapter of my dissertation that remains unpublished. So I figured if I talk enough about it, I have to get it out into the world. But what I'm going to tell you today is about these single-celled protists called planktic foraminifera. And you're looking at those on the screen, and you're seeing a big one that's right here. And this was taken using a scanning electron microscope. It's a really strong microscope. And these creatures are about the size of a grain of sand. So let's dive in. So foraminifera are single-celled protists. They're not animals, they're protists. They belong within zooplankton. And they create these calcium carbonate shells, or what we call tests. So their shells are made of the same thing that seashells are made of that you would find on the beach. And they come in two main varieties or two main flavors. There's the benthic foraminifera. Those are ones that live on the bottom of the seafloor. And what you're seeing on the upper right side of the screen, those are benthic foraminifera that live on a reef ecosystem. So pretty shallow water, but they're very beautiful. These small, tiny shells. And there's planktic foraminifera. Those are the species that I dominantly work with. Now, they live in the surface ocean, so the really warmer parts of our ocean. We call it the mixed layer. I wish I could point. But it's pretty much that upper part of the water column down to about 200 meters or so. But there's also species that live along the thermocline region. So the thermocline is that area of our ocean where we transition from very warm surface waters to the colder, deep ocean where temperatures are pretty constant at around 37 degrees Celsius or 37 degrees Fahrenheit. So the planktic foraminifera, they live in our global oceans today. They have for about 175 million years. And they are distributed from very high to very low latitudes. So at the bottom right of the screen, what you're looking at is a living planktic foraminifera, and all those spines that are coming off of it, those help it trap organisms to eat. So this is a single-celled protist, and it is feeding on a copepod, a multicellular animal. So they are small but mighty. So planktic foraminifera, they don't have any paddles like fish, nothing like that. So to disperse or move across our oceans, they're really at the mercy of ocean currents. So I want to draw your attention to the bottom left of the screen. This is just our modern Earth today. The continents are blacked out, but those red and kind of pinkish yellow circles on there are all of our gyres and surface ocean circulation systems. So it's really these surface ocean currents that the planktic foraminifera, that's how they move or distribute from one area of the ocean to another. The cool thing about foraminifera is that they will only establish viable populations and live where the conditions in the ocean are right for them. So now I want to draw your attention to the bottom right of the screen where that red box is around this map. So what you're looking at in the darker gray is the distributions of populations where these organisms lived. That one specifically is a population of Polyneatina spectabilis. Now that's a species that lived from about 3 to 4 million years ago, and it only lived in the central Pacific Ocean, nowhere else in the global ocean. But its descendant species that's still alive today, Polyneatina obliquolaculata, and the light gray distribution, that lives across the equatorial oceans today. So this is just highlighting that these species in the past have only lived where the environment and environmental conditions are right for them. And then some species have a more global distribution where they can live. Foraminifera are also very, very sensitive to ocean temperatures. That there are several studies that have been published that indicate that temperature is the one thing that controls their distribution where they live in the global ocean. So what you're looking at in the middle of the screen is our surface ocean map. And all of those little dots represent different occurrences of foraminifera, different species. The warmer colors indicate where we have more species, higher richness, just the number of species that live there. The cooler colors represent where we have fewer species living. So you can see in the tropical areas, we have a lot of different species that are living there. But as you move to the high Arctic or Antarctica, we have very few species that live there. They don't like the cold. And you can even see that our tropical species in the upper right of the screen, they're very cool by their shapes. Some of them have these like hand-like appendages coming out of their chest. Some of them have these other, what we call these chambers that are very elongate, like digits. And then if you look at the more temperate water species at the bottom left of your screen, notice that these are a little more conservative in their shapes. They don't have all these wild appendages. So we can actually see the differences in these warm water species versus cooler water species just by looking at their shells. So because foraminifera are very sensitive to temperature changes, and because they follow and disperse based on those ocean currents, this makes their fossil record really, really awesome to study how these things evolve in the oceans from the past until today, and also for biogeographic analyses. What causes these species to move from one place to another, and what enables them to live in one place and not another? And that's really what my area of focus is. One of the neatest patterns of distribution that foraminifera exhibit is called bipolarity. So foraminifera and other marine protists exhibit this. It's when you have populations in either hemisphere, but that does not occur in the tropical regions. So it's also called antitropicality. Antitropicality. And we see this pattern of not dispersal. We see this geographic pattern of these populations living in either hemisphere, but not in the tropics, in bacteria, viruses, and also these things called radiolarians. They're very similar to the foraminifera, but they actually make their tester skeleton out of silica or quartz. It's more commonly known as. So what you're looking at now on the bottom right of the screen is a figure from Steppenjans and others in a paper they published in 2013. All of those little black squares and dots represent the 3 different species of radiolarians that are on that figure. Note that they occur in the high northern latitudes, the low southern latitudes, but they do not occur in the equator. So these species do not like warm waters for one reason or another. So there was this paper that was published in 2000 by Kate Darling and her colleagues. And what they did was do genetic analyses of 3 living species of planktic foraminifera. They looked at species from the Arctic. So this figure at the bottom left kind of shows where they collected, and Antarctica. And what they were really looking for is how common is bipolarity, this pattern of antitropicality in the planktic foraminifera. We know it occurs probably in the geologic past and for other marine protists, but like actually how common is that today? Can we see this? So what they did, they captured these live foraminifera off the coast of Greenland, and then they also captured them off the coast of Antarctica in really cold waters in either hemisphere. And they conducted genetic analyses on 3 species of foraminifera. The first one is Globigerinoides beloides, Tuberotalia quinqueloba, and the third one was Neogloboquadrina pachyderma. Don't worry, I won't make you repeat those names later. What they then did was kind of make a family tree of their genetic material to determine who's most closely related to who. So you all have probably heard of things like 23andMe, like those genetic testing things you can do, and now they have them for like dogs and stuff. That's basically what they were doing for the foraminifera. We're all the same species, right, of humans, but doing these genetic analyses shows us who our most common ancestor is, like in our family tree. So that's exactly what they were trying to accomplish here. They wanted to see if those populations off Greenland and Antarctica had exchanged genetic material very recently, just like, you know, your mom and dad created you and so on and so forth. So that's what that figure on the right of the screen is showing, just that genetic family tree. What they found was that within all three species, they were all genetically very closely related. So think of this as like finding your brother or sister in another hemisphere from you. That's essentially what they determined. So those Arctic and Antarctic populations had actually exchanged genetic material very recently. And what they determined is these species somehow, to reproduce, had to make it from Antarctica across the equatorial ocean into the Arctic, and vice versa, from the Arctic across the tropical ocean to Antarctica. So, and that happened very recently in the geologic past, they determined probably in the last 200,000 years. Further, they went on to hypothesize that, well, this genetic exchange between Antarctic populations and Arctic populations had probably been going on since a time we call the Miocene. So that's from about 16 to 18 million years ago. So this now begs the question, how did these planktic foraminifera that exhibit this bipolar distribution, how are they crossing those tropical and subtropical oceans if they don't like the warm waters? What are they doing? So in her paper, Kate Darling and Dick Norris and his partner De Vargas, they also published a paper the same year. What they hypothesized was that these species of foraminifera were using upwelling zones. So upwelling is when you have winds that are pulling the waters away from the coast, and you get very cool waters from the bottom ocean pulled to the surface. It upwells from the bottom. So they were using that upwelling along these coastal regions as kind of like these stepping stones to hop from one place to another to get from one hemisphere into the other. So that's what I'm kind of showing on this map from NOAA at the bottom right. In red on that map is all the places in the world today where we have these cool water upwelling, where very cool water is being pulled to the surface ocean, and it's a cooler area off the coast. And I've just plotted the little Globigerina boloides on here to kind of demonstrate how it would do that. They further hypothesized that this kind of pathway, this kind of using these upwelling zones as stepping stones, probably happened during cooler periods in Earth's history, such as during glacial periods when we have ice that was much more extended across our continents and the Earth was much cooler. So the goals of this study were actually pretty simple. We wanted to see if planktic foraminifera that exhibit this bipolar distributions in the Arctic and Antarctic, if they did use upwelling zones to disperse across tropical regions. If they do these dispersal events occur during cooler periods in Earth's history? So to do that and to answer those hypotheses, we went to the fossil record of these foraminifera. So we're going to focus on one genus of foraminifera called Globocanella. I'll talk a little bit more about those in a minute. And we're going to reconstruct their dispersal history through periods of time called the Neogene and Quaternary, so about the last 19 million years of Earth's history. So this is a big slide. I just want to step you through it. It's not as intimidating as it may seem. There's a lot of data on here. It's very geologic. So on the right side, this is our geologic timescale from 66 million years ago at the very bottom to 0 million years ago till today. And what I've got highlighted by that red box is an interval of time called the Neogene. So this was from about 23 million years ago to, we'll say, about 2.5 million years ago. Now, what you're looking at in the middle of the screen is a chemical signature that we obtained from benthic foraminifera that live on the bottom of the seafloor. And what that chemical signature tells us is a temperature of the bottom ocean waters through time. So you'll note that if that curve is trending towards the left, towards your left, it's getting cooler, there's more ice on Earth. But if it trends towards the right, that means Earth was warmer with less ice. So during the Neogene period, note that that line was trending towards the left. So Earth was cooling down. We had a lot of ice growth on Antarctica, and there were few global warming periods that punctuated this, global cooling periods that punctuated the warming. Then we move into the Quaternary. So this is about 2.5 million years ago till today. This is when the Earth got really cold and we get what we call interglacial and glacial cycles. So the Earth went from very cold, very warm, very cold, very warm. And that happened on timescales of about 100,000 years. But essentially what we're seeing during this time period is Earth coming to its more modern day configuration with respect to temperature gradients between the equator and the poles, the amount of ice that we have at the poles like today, and the surface ocean circulation patterns that we have today. Those were all coming into their modern day configuration. So there was a lot of events that happened in the last 23 million years of Earth's history, and I've plotted those now on that chemical curve that tells us about warming and cool periods through Earth's history. There are two events only that I want us to kind of pay attention to. The first is a Miocene climate optimum. Now, this took place from about 17 to 14.7 million years ago. And it's outlined here by that red box. So this is when atmospheric CO2 got to about 500 parts per million. Today, we're flirting around 420 or a little bit over 420 parts per million. Surface temperatures were about 3 to 8 degrees Celsius warmer than today. And right after that was the mid-Miocene climate transition. So this occurred from about 14.2 to 13.8 million years ago. And this event, this cooling event, was due to expansion of Antarctic ice sheets. So Antarctic ice got big. That led to the Southwest Pacific Ocean, surface ocean, to cool by about 6 to 7 degrees Celsius. So big warm up, big cool down. And that's the events we're going to talk about. I don't want to talk about the rest of the events because we'd be here all night and the batteries won't last that long. But throughout the rest of the Neogene and Quaternary, essentially what we're looking at is continued cooling of the Earth, continued ice growth in both hemispheres, and increased equator to pole temperature gradients. So the equator stays hot, but their poles get colder. Promised I would tell you about the genus Globocanella, and they're my favorite because I think they're absolutely adorable. So there's only one species that's still alive today, and that's Globocanella inflata, kind of down there at the bottom right. They inhabit thermocline waters in our mid-latitude regions, so defined by about 30 to 60 degrees north and south hemispheres. And if we look at their fossil distributions, where their fossils occur in the global ocean, they have a largely anti-tropical distribution. So they're occurring at the high latitudes in the northern hemisphere, high latitudes in the southern hemisphere. They don't like that warm weather in the tropics and subtropics. And this genus continuously evolved during the last 19 million years. So all these 6 species that you're looking at evolved at different times throughout the last 19 million years. So we're going to use these 6 species to infer kind of dispersal dynamics. And when I say dispersal, I really mean movement from one place to another. So think of like living somewhere, selling your house, moving to another place, buying a new house, just like that. Across the tropics, how did they move across the tropics? Okay, so we have this wonderful database that we call Neptune. And it is a database where we can store and then download all the occurrences of planktic foraminifera species from our global ocean. So these are all collected from deep sea sediment cores where we go out in boats and drill down through the ocean sediments. And then we look at those sediments, we extract those fossils, and then we can determine where they occur through time. So I downloaded the data for the 6 species that I wanted to use, and I ended up with 32 sites that were distributed across the global ocean where these species occurred. And I've plotted those sites on a modern day sea surface temperature map. So that's what you're looking at the bottom of the screen. The warmer colors indicate warmer temperatures, cooler colors indicate cooler temperatures. And these sites were specifically chosen as well because they occur from the tropical oceans into the high northern and high southern latitudes in those tropical water masses. Sorry, subpolar water masses. To discuss the data a little easier, because I don't want to talk to you in about like 32 different sites, what we did was split our ocean into 9 different regions. So I've listed them here, such as the Northwest Pacific. And you can see the Northwest Pacific on the upper right side of the screen, circled in red as well. So I kind of tried to split those regions according to latitude and kind of ocean temperature, but it's imperfect. But that's how I'm going to talk about these regions. Okay, another kind of big figure here. What I then did was plot when each species occurred at a different region. So here's our 9 regions again, through time. So let's zoom into one of them, and I'm going to show you a little bit more about what you're looking at. So these are the first occurrences of Miosia. So this represents the first time that species appears at one of the sites. So what you're looking at on the y-axis is age in millions of years. For this species, it goes from about 19 to 9 million years. And then on the x-axis at the bottom, you're looking at latitude. So on the left is -60, so southern hemisphere, equator in the middle, and then all the way up to about 50 degrees north. There's a few things that I want to point out here. So I did plot age error, and I don't want to talk about age too much and all that. You can ask me about it later. It's kind of a lot to get into. There's a lot of uncertainty of when a species first occurs at a site. So I should also mention all those 9 regions are represented on this figure by a different color and a different symbol. So that's what I've plotted on here. So all those different symbols and their different colors represent the different regions, and then the number beside it represents the site number from which it came from. So if we look at the site 747A from the Southern Ocean, over 2 million years of uncertainty, which means that species could have occurred any time at that site within 2 million years, but we just take the midpoint. The second thing is that there are large differences in when a species first occurs within a region. So what I've put this orange box around is all of those, the times at which a species first occurred in a region for the Southwest Pacific Ocean. That's represented by those orange circles. All of these sites have about 3 million years error associated with them. That means for one region in the Southwest Pacific, species were occurring at those different sites about 3 million years apart. And that may be weird. So both of these factors, these large differences when a species first appears in a region, and also that large error makes tracing their dispersal, their movement pathway through time a little tricky. But that's essentially what we did. We kind of traced where they occurred through time just by simply saying, okay, they appear first in the South Atlantic, then the Southwest Pacific, then the Southern Ocean, and then up here, okay? And if anybody has questions or is unclear, you're more than welcome to stop me, because I know this is like kind of weird looking. It'll make more sense hopefully in a minute. So what I then did was trace out where and how those species moved across the global ocean onto a modern day sea surface temperature map. So what you're looking at are the traced out dispersal or movement patterns for 4 of the 6 species through time. So we have Praescutula up in the top, Myotumida, Myosia, Conomyosia. So you'll note that all of the sites that they occur at are denoted by like tiny white dots. And there's a number beside that dot. You don't need to be able to read it. I'll show you more in a minute, but that's the time at which that species first appeared in that region. So I want to point out some big scale patterns for you. The first thing we found is that all 6 of these species first evolved in the Southern Hemisphere, which is really, really neat, because that's the first place on our Earth where ice first appeared and became quite large. So I'm actually thinking that a lot of species first evolved in the Southern Hemisphere because of all that ice and the cooler waters that developed, and these species took advantage of that. They moved into what we call a new niche space, a new space that allowed them to thrive and live where other species did not currently live. Once they evolved in the Southern Hemisphere, they then jumped on the Antarctic circumpolar current. So the ACC is this ripping current that goes around Antarctica. It's a really fast current because there's no continents to obscure its path. And they kind of use this as a carousel. So I'm from Binghamton, New York, and I don't know if y'all know this, but we have a claim to fame globally. We are the carousel capital of the world. So I'd be remiss if I did not mention a carousel and show it on the screen. So they're kind of using this as a carousel. They're jumping on the carousel where they evolve, riding the carousel around, and then jumping off in another ocean basin. When that species jumps off into a new ocean basin, it's then using eastern boundary currents. So the eastern boundary currents are denoted by the kind of purple square on here. They occur on the eastern side of ocean basins and also by western boundary currents. So western boundary currents are highlighted by those white boxes, and they occur on the western side of ocean basins. So like the Gulf Stream that comes by the East Coast, that's a western boundary current. And all of this happens during and also after global cooling, which is quite neat. Okay, but let's get to the heart of that research question. Do planktic foraminifera that exhibit a bipolar distribution use upwelling zones, these cool water zones, to disperse across the tropical regions, to move across those tropical waters? And if they do those dispersal or movement events occur during cooler periods in Earth's history? So I'm going to laser focus onto two of our other species, Praescutula and Myosia, and talk about their dispersal histories to answer this question. So we're going to start with Praescutula. So I'm going to explain this slide, so hang with me for a minute. So what you're looking at on the left side of the screen is that geologic timescale. Again, from this time, it's from 19 to 0 million years, 19 at the bottom to 0 at the top. You're looking at that geochemical, that chemical data in the center that denotes times when Earth was warmer and cooler. And the Miocene climate optimum is outlined by that red box. The mid-Miocene climate transition, the cooler period, is outlined by that blue box. There's also that modern day sea surface temperature map. And notice that I've put a little image of the fossil on there. And I'm also I have text up here at the top. I'm going to show you where that fossil evolved. So I have the arrow pointing at the timing at which that fossil evolved. As I step through, I'm going to put an arrow where in time that species moved. I'm going to show it on the map, and I'll show it to you also in words. So Praescutula first evolved in the Southwest Pacific, in that region where that fossil is plotted, about 18.5 to 20 million years ago. It then moved into the Eastern Equatorial Pacific around 14.1 million years ago. So notice on the geologic timescale and chemical data that this is during the mid-Miocene climate transition, that cool period. From studies that have been published by other scientists, this is a time when we have increased equatorial upwelling, so the bringing of cool waters to the surface ocean due to the Earth cooling down because of ice growth on Antarctica. So I want to show you this a little bit more in detail. So what you're looking at on the left side of the screen, upper left, is another image of Earth and its sea surface temperature. And I've put a blue box around the Eastern Equatorial Pacific. So in the Pacific and in the equatorial regions, winds blow from the east to the west. Sorry, I know I'm backwards from you all. And what that does, it pushes warm water away from the coast of South America, and it pulls cool water up to the surface. So notice where that blue box is, sea surface temperature is a little colder than that surrounds it. This box diagram is showing you exactly what's going on. So it's showing you the thermocline. That's that area in the ocean where we have cooler waters. And that thermocline is tilted a little bit to the east because it's being pulled up to the surface by winds. This also causes a lot of nutrients, what we call chlorophyll, to also come to the surface ocean. So there's a lot of food and there's also cooler waters, and that's great. So this is what happened. This kind of process intensified when the Earth started to cool down, when Antarctica grew ice. What then happened is this species was then able to disperse and move into the Northwest Pacific by 13.39 million years ago. So the data from this species and its dispersal pathway, its movement pathway through time, indicate that, yeah, it actually did use this upwelling process as the stepping stone to get from the southern hemisphere into the northern hemisphere. And that was really neat. We're going to play the same game with Myosia. So again, different species, but you've got the map, you've got the geologic timescale on the left, and then I'll put in words what's happening. So Myosia evolves in the South Atlantic Ocean in the southern hemisphere at about 18.5 million years, kind of near South America. And then it jumps on the ACC and moves to the Southwest Pacific by 17.7 million years ago. It then disperses into the Western Equatorial Pacific. So this is kind of north of Australia, New Zealand. And it kind of hangs out there for about 16.3 to 13.7 million years. So notice this is still during the Miocene climate optimum, a time of global warmth. So actually my PhD advisor was the one to work on this site with one of his other first PhD students. And he said that the occurrences of this species in the Western Equatorial Pacific is, and I quote, rare as hen's teeth. So it's like that species was trying to move across the tropical ocean, but it wasn't able to establish a robust population. The waters were just too warm. Again, the conditions were not right for it to establish a population, but it was trying to. And we have just enough fossils from the sediment record to kind of support that hypothesis. But then what happens is about 13.7 million years ago is that that species is able to then disperse and move into the Northwest Pacific Ocean. So cross the equator and move into the Northern Hemisphere. Again, this is during the mid-Miocene climate transition. And we also have chemical data from prior scientists, Gasparini and Kennett, that indicates during this time, the thermocline region of the ocean in the Western equatorial Pacific actually was cooling down by a lot. So I'm going to show you another box diagram. So I've kind of already showed you the right part of that box diagram, where we have those coastal winds and upwelling. The winds push the warm water to the west, cool water is brought up in the east. So you're looking at this entire box diagram across the entire Pacific Ocean now. Notice on the left side of that box diagram, we have all that warm water. So where that purple arrow is where that site was drilled, the occurrences of the species were. And essentially what happens, I don't want to explain all of this, but I just want to draw your eye to this big gradient that develops. What these scientists did were look at the temperatures between the thermocline region and the surface ocean, and they increased. They also looked at the temperature gradient between the bottom ocean and the thermocline, and those increased. In other words, what they were showing was that the thermocline region of the ocean cooled down. Even though the surface ocean got very warm, the deeper part of that ocean where these species that we're talking about can still live got very cool. So this data from Myosia then also show that species use cooling thermoclines as an additional strategy to cross that equatorial region and make it from the southern hemisphere into the northern hemisphere. So let me just conclude a little bit here and recap. So Kate Darling and colleagues in 2000 and Norris and DeVargas in 2000, both of their papers, they hypothesized that species used upwelling zones along coastal regions as kind of stepping stones to make it from one hemisphere into another and across the warm tropical oceans. And that this may have occurred during cooler periods in Earth's time. So our first question was, do these planktic foraminifera that exhibit this bipolar distribution, they like to occur in high latitudes in the cooler waters, but they don't like those very warm waters, did they use these upwelling zones to disperse across the tropical regions? And we found that yes, species did utilize that cooling thermoclines to disperse across equatorial regions. And if they do these dispersal or movement events occur during cooler periods in Earth's history? And we found that yes, this trans-equatorial or equatorial movement of these species occurred during expansion of Antarctic ice sheets when the Earth really cooled down and ice expanded during the mid-Miocene climate transition. Okay, so just to acknowledge, this talk, I was able to be here because of the International Ocean Discovery Program. It's a program that allows scientists to go out on a huge ship for 2 months, pampers us by doing our laundry, cooking for us, and all we have to do is like really cool science. It's an awesome gig. And the Cushman Foundation for Thorium Research, which funds research into foraminifera. And I was actually able to do this research because of Joanna M. Riesing. She had a fellowship developed in her name. I feel like she is a kindred spirit because clearly she loved to hang out with her cat in gardens while barefoot, and I can totally connect with that. So I am more than happy to answer any questions you may have and have conversations after this talk if you want to delve in deeper into any topics. Thank you all. And if you have a question, raise your hand. I'll come bring you the mic. Yes.
Okay, I'm not a biologist, but I'm curious, when they were identifying these different foraminifera, did I guess the structure change through time? How difficult was it to identify the particular species?
So how difficult was it to identify different species? So you're hitting on a field called taxonomy, and it's who's a species and who's not. And I'm a taxonomist. I do this as part of my job in research. It actually can be really hard because of the resolution at which we can see the fossil record. We can actually see species evolving from one species into another. So commonly we get this like what we call intergradation. So it's not quite this species, it's not quite this species, but it's somewhere in between. And we see characteristics of both. So when we see that, we know we're in a transition zone. We're in a time of evolution. So we kind of have to make a judgment call of who's who and who's what. But when a species have fully outside of that, it's kind of easier to identify a species. But because these are plankton that are the size of a grain of sand, you've really got to tune in your eyes. So great question. It can be really hard or it can be kind of easy. I'm going to go to you and I'll come back.
Hi, thank you. So kind of going along with that, you showed us that there could be 2 million or 3 million years of error when determining when did a species first appear. What are some of the factors that contribute to that error?
Excellent question again. So what are some of the factors that lead to kind of that large age error? So I want to go back. Sorry, just hard to see this. And go back to this. There could be a lot of factors. So the deep sea sediment record can sometimes be incomplete. We can have missing time from the sediment, and that can be due to the ocean, bottom ocean becoming acidic. At that point, it dissolves all of these fossils. We can also have that sediment washed away by very strong currents on the bottom of the ocean. It could also be due to, and this is the case for one of these species, somewhere in here. Maybe I didn't plot it for that species. Some of these don't come from the deep sea. Some of these come from uplifted outcrops. So rocks on land that used to be in the marine environment. And that's from New Zealand. So New Zealand, a lot of it was underwater, and those rocks are now exposed on land. So sometimes we just don't have great age control. We can't get precisely the age of the sediment. And that can also lead to huge, huge age errors. So good question. You had a question?
I did, but I'm not sure it's a good question. How long does an individual, how do I say it, foraminifera live, and how many of them are out there in order to span millions of years in the transition?
So how long do they live and how many are there? Okay, so how long do foraminifera live and how many are them? So a foraminifera actually has a really short lifespan, unfortunately, a couple weeks to maybe a month at most. Yeah, it's sad. RIP. But there's actually not that many. There's about 1 foraminifera per liter of ocean water. So over time, they collect and collect by the millions over, on the seafloor. But there's not actually that many in the open ocean. They actually, are a little spaced out. Great question.
So with the climate change that we're now seeing as an effect of global warming, how might that affect foraminifera in the modern era, or will we not see very much of an effect because historically this has taken millions of years to show any change?
So thank you so much for asking that question about climate change and how warming today is going to affect foraminifera. The short answer is we don't know. If you take this research and rewind the clock, there's really no way to do that, right? So we're not sure. But I will tell you some pieces of data that we do have right now because it is a very active and ongoing area of research. Foraminifera are very important to study. There's zooplankton. They're not at the very bottom of the food chain, but they're near the bottom. So understanding how climate change in the ocean affects them scales up the food chain, right? To our bigger predators like sharks, whales, everything that depends on these critters. There has been research done. So there was an expedition called the Challenger that went out in the 1800s. So this was before climate really started to change and before humans had a big influence on the climate. And they collected sediments from the bottom of the seafloor. And these were sediments that were really modern. What they did was called a box core. They kind of like dropped a box to the bottom and just did a scoop of sediment and brought it up. So we call that modern. And it could have been only, mixed by a couple hundred years or so. What my friend Lindsay Fox did, she went back to those Challenger expedition samples. They were stored at the Natural History Museum in London. She looked at those samples and the foraminifera within them, and she compared them with modern foraminifera that were collected during the Terra expedition. That was in 2009, I think, so recent, right? These foraminifera were living under climate change. And she looked at the thicknesses of their test or of their shells to see how that thickness changed from those collected before climate change was really a factor to now. She found that under climate change, the foraminifera shells are thinning by about 30%. And that's also something that we find from these marine gastropods called copepods. They live off the coast of Antarctica. They cannot deal with the waters becoming more acidic because their shells are starting to dissolve. So it's harder for them to make their tests, their shells. And even when they do, because the waters are becoming more acidic, they're dissolving away. So there's, again, a lot of uncertainty, but we do have some data that shows that under climate change, because of ocean acidification, foraminifera are already suffering from that. Good question.
I have one that's kind of similar. I noticed the ones on the southern part of the world were round, and in the middle you had the strange shapes. Could it be for increased surface area for heat distribution? Because you saw the transitional of the myosea, that when it was in the tropical water, it actually changed shape a little bit.
So you nailed it. So because these species are living in more warmer waters and they're living at the surface ocean, so that one's actually living in the deeper thermocline region, but these three are living in the surface ocean. So they need to stay light and they need to stay buoyant. So a lot of these species have what we call spines that come off. And I showed that very early in the talk from a living foraminifera. It had spines and it was eating a copepod. Those spines help it stay afloat. But the other really cool thing about foraminifera, especially this one, Ruber, Beloides had it too. Those spines also hosted photosymbiotic algae. So they have algae that live in those spines. The algae kind of help the foraminifera with food production, and the foraminifera provides that algae with a place to live. So it's a fully symbiotic relationship. But yes, and then the ones that live in the thermocline region, like the globocannellas, especially Neoglobocardrina, whoops, over here, they're very thick. Their tests are much thicker, they're much more robust because they need to sink into the water column and stay within the thermocline region. So yeah, good observation, you're exactly right. Any others? Any Zoom questions?
Answered all their questions.
Cool. Awesome. Well, let's give her another big round of applause. Thank you guys so much for joining us this evening. This is just the first of our Naturally Speaking for this year. So every third Thursday of the month, we have a new speaker. So next March on the 21st, we'll kickstart our reptile and amphibian weekend with a speaker that's going to focus on Virginia amphibian species. So we hope you guys can come back and join us for a future event. Thanks so much. Have a great night. Yes. And also, if you're interested, we do have a couple microscopes set up with some plankton that we collected earlier today. So if you want to get a little bit more plankton nerdy with Dr. Lamb, please feel free to come check it out.